Welcome to this joint webinar between CISSOID and Silicon Mobility. This webinar will focus on optimized pulse patterns, a novel method of driving a motor with the advantages that you will see later on. Just a brief introduction. I'm Mike Sandik with CISSOID. Our company was founded in July 2000. We're located just south of Brussels in Belgium, and we have a fabulous model of business.
And I'm Patrice Brutinel. I'm Technical Sales Director at Silicon Mobility. We are a semiconductor and software company located in south of France, incorporated a little bit more than 10 years ago, and we have been acquired by Intel 2 years ago. So we are now an Intel company running independently from Intel. And yeah, I'm very pleased to present the OPP that we have implemented on our solution and which is available on CISSOID system.
Okay, thank you, Patrice. So as a brief overview from our side, we'll present mainly the hardware platform this software is running on. So those are our inverter control modules, the control processor, and a brief intro to the software itself. And then Silicon Mobility will go into what optimized pulse patterns are and what benefits they bring. And afterwards, we have a question and answer session. If you do have questions that come up during the webinar, feel free to enter them into the Q&A queue, and then we can answer them afterwards. So CISSOID products, very briefly, we have on the one hand the semiconductors and power modules that we traditionally do, and on the other hand, we have more system side solutions as gate driver boards, inverter reference designs, and even full inverters, where we qualify motors on those solutions and go into novel systems like high power charging, battery disconnect systems, and so on. Now, the silicon carbide inverter platform was built on what we call an intelligent power module. This is a three-phase, so 3 half bridges in silicon carbide MOSFETs with the gate drivers on top of it. We developed the motor control board in cooperation with Silicon Mobility, where you see the Silicon Mobility processor on top of it, of which we'll talk a little bit more in detail. From that, we evolved a reference design that is a ready-to-go inverter. Actually, you can plug this into a vehicle and start testing. Of course, running the state-of-the-art software, of which this webinar is the focus today. A little more on the control processor, the ACU T222, as it's named. This is a processor dedicated to motor control. Our module gives several interfaces to resolvers, encoders, temperature sensors, of course, the necessary current sensors, debug and trace interfaces, and so on, and runs the adaptive control app by Silicon Mobility, where you have an API interface allowing you to customize the software according to your own needs. The processor itself is a very fast real-time processor. It has an advanced motor event control unit, which is specific in that respect that it has a flexible logic unit, a FPGA-like structure that allows to do major parts of the control loop in hardware. And this means that you reach very fast processing times of whatever happens in the motor. So fault detection, correction, and containment happens within very brief periods of time. Also offloading the processor, meaning you don't need a very high processing capability processor, plus you keep some of the processing power for your own application. On top of which, because of the FPGA structure, it makes it very predictable in timing. Now I hand over to Patrice on the adaptive control solution.
Thank you, Mike. So the adaptive control solution is is a full stack solution that we bring to our automotive customers, so tier 1 OEMs that want to design their own control applications. So yeah, so what there is in that adaptive control solution? We combine semiconductor, tooling, library, and application software. So the adaptive controller unit are the pillar of our offer. As Mike briefly introduced, this semiconductor, the adaptive controller unit, are a family of device enabling to cover from entry range to high-end real-time computing application like inverter control, DC-DC control, but also X-in-1 application, domain control, as well as zonal applications that require high level of real-time computing, high level of functional safety, technology, cybersecurity, as well as the ability to run in parallel and guarantee the deterministic execution of several applications. So the adaptive controller unit, it's designed in automotive technology and is also ASIL-D capable. So it combines accelerations, hardware acceleration, flexible, that allow to integrate advanced control algorithm and to run them at high frequency. To support application development, we bring to our customer what we call the adaptive control composer. It's a design environment that supports model-based design, automatic code generation from the model to ease the integration of complex algorithms, control law, as well as full application into our device. It comes also with a set of software, design kits, and debugger, high-speed real-time trace to ease application development and calibration all along the development process. Together with the adaptive control composer, the design environment, we bring also libraries, set of libraries that we call adaptive controller library. They are MATLAB Simulink libraries that will help customers to quickly build their own control application, their own algorithm, and integrate fast into our adaptive controller unit semiconductor platform. And the last stage of our offer are full application software. So as today we have integrated in the CISSOID application, which is the adaptive controller application for inverter and motor control that we call AC App Inverter. This is a full set of motor control software, fully qualified, already in the field, and that support advanced algorithm to get best performance and to push the performance of the electric powertrain and the electric vehicles. And this is what we are going to see in the details and how we bring the optimized pulse pattern using and leveraging all that state-of-the-art solution. Last word on the adaptive control solution. It's a full automotive solution, qualified ASIL-D, ISO 26262. The software is following the automotive SPICE level 2 standard development process. So we can move forward, Mike, please. So what is the OPP that we have successfully implemented on the ACS? So OPP stands for Optimized Pulse Pattern. It's a modulation technique that you can compare with legacy modulations that you find today on the market, which are the SVPWM, DPWM, or six-step full wave methods, which are all time-based modulation, and the OPP differ from the fact that it's an angle-based modulation. So angle-based meaning that you are removing all the PWM carrier. You don't have any more a fixed frequency carrier, but you locate the transistor switch at any angular position. So it gives you a full freedom to place the switch by removing the fixed frequency and the symmetry on the gate pulse. By this way, we can define optimized pulse pattern, which are a list of switch angle within the range of 0 and 2p. Use it to control the inverter and the motor. So we have developed a technology and a tool that we call the pattern generator that will allow to generate pattern optimized for a speed and torque range, as well as a modulation ratio. And we can optimize the pattern in function of different criteria. That could be to reduce the energy losses that you have on the inverter and the motor, as well as to reduce the THD, to have a better quality of phase current signal, to reduce ripples on the DC bus, as well as to remove harmonics that could be responsible for NVH at system level. So with the OPP, we demonstrate the ability to reduce at the same time losses at the inverter and the motor losses and the motor. So here, by bringing a more efficient system, OEM can get a lot of benefits in terms of power dissipation. So you can reduce the cooling, but you can also reduce the size of the battery. So if you have a more efficient system, you can deliver the same range with your vehicle with a smaller battery, or you can keep the same battery capacity and extend the range of the vehicle. So this technology, by improving the control of the gates and the electric machine, bring a lot of benefits for the OEM, and it's the reason why today it's something that OEMs are really willing to integrate in their electric powertrain system. So we can move forward and to go a little bit more in the details. So in that slide, we show how we compare an OPP and the SVPWM, the legacy modulation, which is today broadly used in the automotive market. So as you can see, the OPP on the left is not anymore a time-based modulation. So we are really switching based on the position of the electric machine, and this allows us to really optimize the switching. So we switch at the best time to achieve the criteria. And here, what we simply demonstrate is the ability to reduce drastically the switching with the OPP compared to the SVPWM, while improving the quality of the signal. So we reduce the switching. So we reduce consequently directly the inverter switching losses, as well as we improve the quality of the signal. We improve the THD of the phase current signal, allowing us to push also the performance of the electric machine. So we reduce the losses at the inverter and at the electric machine level. Yeah, we can move forward. So the benefits at system level, providing a system which is more efficient, so with less losses at the inverter and motor level, will allow us to deliver more efficient powertrain. So we have demonstrated on concrete use case the ability to push the efficiency by 3 to 5% on the most critical WLTP pain points that you can convert in kilowatts of battery energy saving from the losses. So we can reduce by the range of 30 to 50% on the overall of the total losses. So with a more efficient system, you can also expect to reduce the size of the battery. So you have the choice, either you deliver more mileage, I would say, more. You can extend the range of the vehicle, or you can reduce the size of the battery by 20% to achieve the same level of range. We can also reduce the BOM. So we show the ability to improve the quality of the signal, to reduce the DC bus ripples that allow us to reduce the DC capacitance, which has a direct impact on the bill of material of the inverter. We show the ability to reduce the losses, so you can reduce also the cooling of your subsystem. As well as we have, thanks to the OPP, we can really implement high-end over modulation technique that will allow to push the performance of the electric machine, so to deliver more torque with the same level of energies, allowing us to support motor downsizing, so reducing the motor size to deliver the same power, or enabling our customer to deliver more power with the same electric machine. So at the end, for the OEM, it means that their car can deliver a longer range, as well as be lighter and cheaper. So how do we implement the OPP technique on using the ACS? There is two consecutive phases. The first one is offline. So we have designed what we call the optimal pulse pattern generator, OPP generator, which is a model-based predictive solution that will generate the patterns to be applied by the control in the field. So this pattern and this OPP generator is based on loss models. So we configure these tools with accurate data from the inverter and the electric machine, and we are inputting the optimization criteria that we target. That could be reducing the energy losses, that could be to improve the THD, to remove harmonics, to reduce DC bus ripple. And this tool will generate a set of pattern tables to be applied by our solution. So the second phase will be to integrate our semiconductor with our motor control software that we call the AC app inverter, and that is able to commute smoothly from different modulation techniques. So it supports SVPWM, DPWM, and OPP. So depending on the torque speed set point, this control solution will apply the best modulation technique in function of the criteria which has been selected by the customer. So it could be SVPWM at low speed, and afterward at high torque, middle speed, or high speed, it will apply OPP patterns. And the beauty of our technology is it's the fact that we can really smoothly transition from different modulation in real time from different techniques to get the best performance of the electric powertrain system. So here we show in the details that flow. So the first phase, which is offline, that will output the patterns and the OPP tables. So the first phase is to do the gathering of the system parameters. So the electric motor model are needed. So usually we input LDLQ, lookup table, IDIQ. We need a stator resistance data and other kind of system information, as well as for the inverter. Of course, we need transistor models, switching losses, conduction losses, DC-link voltage and capacitance characteristics. And as well as soon as we have configured inverter and motor model with the system parameters, we start to define the optimization criteria. So here it could be inverter and motor losses reduction, current ripple reduction, harmonic reduction, so applying selective harmonic elimination, selective harmonic mitigation. We can improve THD and remove NVH. We put also some constraints on the pattern generations, so that could be to generate symmetrical or asymmetrical patterns, to put some limit on the modulation ratio, to input the minimum pulse width that relate to the dead time insertion. We can also put some constraint on the torque ripple and the DC bus ripple. So as soon as models are configured, optimization criteria are defined by the customer, our tool, the pattern generator, will start his work and will generate a complete set of patterns to cover the entire torque speed map in a couple of hours. At this level, we can already perform simulation, have a good idea about the performance that we will get on the embedded system. So we can analyze that pattern, perform model in the loop simulation, extract scoring graph to fine-tune the optimization criteria, as well as to validate the results that we will get at the end. So when the patterns are generated, simulated, validated, we go embedded. And this is what we call the second phase, the inline phase, using our semiconductor and our motor control software. So we configure the software. So the ASIAP inverter software is providing many configuration, calibration parameters to adapt the software and calibrate the software in function of the customer system, the electric machine, the inverter. We can input the tables. So we flash the table into the device, the pattern tables. And afterwards, the control will dynamically switch and select the patterns, the modulation techniques to be applied in function of the torque speed map area. So today, this semiconductor is embedded on the CISSOID inverter, as you know, and the motor control software has been ported. It's fully available, and it provides a very good result, enabling our customer to push the performance of their system only by selecting a more advanced modulation technique.
All right, thank you, Patrice. So,
welcome.
In a few more words on availability and certification, our module is ISO 26262 ASIL C ready certified. It is undergoing to full ASIL C certification. It is automotive qualified, and as mentioned by Patrice, the processor and software themselves are ASIL D level certified.
Yeah.
On top of that, next to the modules, we have the complete reference designs, which are ready to go inverters in a couple of flavors. One is a benchtop, one clearly meant for lab testing with lots of space to access measuring points, and an onboard version to do in-vehicle testing, with an option to even develop that into a custom inverter if required. So it provides a complete platform which is open from the power semiconductors up to the software, completely customizable to your solution. The key takeaways here are that from Silicon Mobility, you have a full stack solution, a state-of-the-art software using optimized pulse patterns, dynamically switching to the most optimal modulation scheme on the fly, significantly reducing inverter and motor losses, with options to optimize for noise and vibration or ripples, meaning you can tune the solution as you require. meaning you can also have a cheaper drivetrain, smaller, more compact, and smoother performing, more quiet for the user. And the hardware and software are available today. So from our end, it's an open and modular platform, allowing fast prototyping. And that is it from our side. Any questions from your side? Let me have a look. So a first question is dead time compensation also active when using OPP modulation? Patrice, maybe you want to answer this one?
So yes, so the daytime compensation is fully managed by our solution. So the motor control software, the AC app inverters motor control software running on the ACU T222 device, manage the daytime compensation, whatever the modulation applies, so SVPWM, OPP, DPWM, and we manage the transition also from the different modulation technique while keeping a good daytime compensation. Yeah, this is something that is fully supported.
Thank you. Another question is, are there any issues when the optimized pulse patterns have a low number of pulses?
No particular issue to generate pattern with low number of edge. Of course, there is a limit. At high speed, it's important to ensure a minimal equivalence switching. So what we can see, it's usually we are able to reduce the switching to 2 or 3 kilohertz while maintaining a very good quality of signal to also reduce the losses at motor level.
Okay, thank you. And maybe a last one, we have 1 minute left on the timing. How long does it take to deploy OPP?
It's a good question. So to deploy our technology, so to integrate our technology in a new design, usually it will take 4 weeks to configure the software, perform the calibration on the real environment, so usually on customer bench, motor bench, and to generate the pattern. Yeah, so overall it takes 4 weeks to have a system running on a customer motor bench and to already start system validation, performance measurements, and also comparison with their legacy solution.
Mm-hmm. And yeah, I can add to that from the CISSOID side, we offer a 1 week on-site support to start going with the solution and help you configure the software and the motor. All right, I don't see any further questions. We'll conclude the webinar here. Thank you for attending, and see you maybe next time. Thank you. Bye-bye.
Thank you very much. Take care.